3.4 is about linear programming. Starting off, we will define linear programming, what it means. And I'll get an email. Linear programming is the process of finding an optimal quantity given a set of constraints.
What is optimal?
Okay, so the process of finding an optimal quantity given a set of constraints. The question is, what does optimal mean? If you remember when we did that farmer problem, the scenario at hand problem where you guys have worked, optimal is the most desirable. Optimal is the most desirable outcome. So if we're talking about income, the most desirable outcome is to make the most income. So in terms of income or profit, you'd want to maximize it. So the optimal answer is a maximum. And in terms of expense or money spent, the optimal outcome would be to spend the least amount of money, so that'd be a minimizing profit. Okay, so for an example, income, the optimal quantity would be to maximize. And for expense, the optimal quantity would be to minimize. We want the least expense. This is just the notes that's leading into how to do that farmer problem. It takes everything that we've done. This one section takes everything we've done the entire year and puts it into a real world problem. So we talked about also says the process of finding an optimal quantity given a set of constraints. So let's also define the word constraints. Constraints are limitations or restrictions. They're limitations or restrictions. So if you remember that farmer problem, the scenario at hand that we did at the beginning of before we started this chapter, his restrictions, his limitations, his constraints was he only had so much land. He only had 162 acres of land available, and he only had so much money to spend. He only had $8,600 to spend in the springtime. The constraints will always be inequalities. If he has 162 acres of land, he doesn't have to plant 162 acres. He could plant less than 162 acres. Yeah, but if he wants to maximize his money, most likely he needs to use all of his land. So the constraints will always be inequalities, and they will always create what's called a feasible region. They will always create a feasible region. The constraints will always be inequalities. They will always create a feasible region. So a new word that's mentioned in that is the word feasible region. Let's define it. If you're to write up all the constraints, every single constraint is going to be an inequality. So if you're to graph all of the inequalities on the same grid, it's going to create some kind of geometrical shape. So it's just like the problem that we did on that paper yesterday, that inquiry paper. If you take a bunch of constraints, a bunch of inequalities, and graph them together, there's going to be a feasible region. There's going to be a region created by all of them, and this is the region. This is the area of the graph where if any point that's inside of here satisfies all of the constraints. Does that make sense to everybody? This ordered pair is a true answer, a true solution for every inequality in problem number 6. So a feasible region is a region of values. A region of values satisfying all constraints. The feasible region is the region of values. It's always going to be a geometrical shape that satisfies all the constraints. And then we also have a term called we're going to talk about what's called the objective function. The objective function is your objective is your goal. So you can think of it as a goal function. If you're doing a linear programming problem, you're trying to, the process of finding an optimal solution, optimal quantity given a set of constraints. So you have some kind of thing, your objective or your goal is to optimize a given quantity. So the objective function is what you are trying to optimize. The objective function is what you are trying to optimize. And then a fact that I want you to write down is the optimal solutions. The optimal solutions always occur at the vertices of the feasible region. Okay, so that's very important. And if you remember, we did the farmer problem, the scenario at hand problem. The optimal solution to that problem was at the vertex of where he used all of his land and he used all of his money. So it's the furthest point that satisfies both equations. And if you can find the points, the furthest points that satisfy both equations, most likely that's going to be your optimal answers. Is there any questions so far? Good. Do a few examples of this. The first couple of examples, I'm going to just give you the graph. There's not going to be any work that needs to be done. So I'm going to give you the graph. It's a straightforward question. Example 1. Given the feasible region, find the maximum value of P equals 2x plus 3y. And let's say you're given this picture. I'm making this picture up. This is not something you should be, where did this picture come from? I'm making this picture up. So we have a point 0, 0, we have a point at 0, 4, we have a point at 3, 4, and we have a point at 5, 0. This is at 3, 4, 5, 0, 0, 4, 0, 0. I'm going to shade it in. That's the graph we're going to use.
Oh, I thought you guys were just making it up.
I am making it up, but that's what we're going to use. I mean, this is a graph that I completely made up. It's not something that has arisen from something in the example that I have written above. This is all information that's given to you. Just going through this problem, guys. We've got linear programming. That's what we're doing. Optimal is most desirable. We've got constraints, feasible region, objective outcome. Okay. This picture is our feasible region. This picture is our feasible region. Okay, the constraints are not told to us. The constraints are not told to us. But anytime you have a shaded in geometrical object, that shaded in object is the feasible region. Your objective function is the goal function, what you're trying to optimize. Is this a problem where we're trying to maximize or minimize? Maximize. What are we trying to maximize? The value of what? We're trying to maximize this function. This is called our objective function. We're trying to maximize p equals 2x plus 3y. That's our objective function. That's what we're trying to find the maximum value of. There's a fact that we wrote right before we wrote this example down. The optimal answers always occur at the what? The vertices of the feasible region. So the largest and the smallest answers will always occur at one of these 4 points. Does that make sense to everybody? So we want to know which point gives us the largest and which point gives us the smallest value. We just take these 4 points and we plug all 4 of them into the objective function. Okay, so here's how we'll do this. We're going to start off at the point 0, 0. And we're going to go to the function p equals 2. What are we going to replace x with? 0 plus 3, and replace y with 0. That should make sense because if you make 0 of anything, your profit, if we can call p it, we can think of p as profit. If you make 0 of anything, your profit is going to be 0. Right? You're not making any money by having 0 objects. So that's the one vertex. Now we're going to go to the next vertex, 5, 0. Doesn't matter the order. You can go to another one. P equals 2. What do we put in for x? 5. And 3 times 0. 2 times 5 is 10. 3 times 0 is 0. 10 plus 0 makes 10. So of these 2 values, which one is our optimal answer of these 2?
10.
The 10, right? So the ordered pair would be 5, 0 is the optimal value. Okay? So then we can also look at the point, look at all the points. 3, 4. 2 times 3 plus 3 times 4. That's 6 plus 12. That's 18. And then the last ordered pair that could be an answer is 0, 4. And it'd be 2 times 0 plus 3 times 4, which is 12. So we've got our 4 possible values. It says find the maximum value of p. So what is our maximum value of p? 18. So we can say the max value of p equals 2x plus 3y is 18. Now, it doesn't ask us where the maximum value occurred at, but if it did ask us where it occurred at, we'd say, and this occurs at 3, 4. So this is not part of the question, but we can write it down. This occurs at 3, 4. Is there any question on this? Now, example 2. Find the minimum value of C equals 3x plus 5y. Typically, when you're minimizing, in terms of business aspect, a very simple example of something you'd want to minimize would be cost. Cost is something you want to minimize, so we're going to use C for cost. Okay, so if we're just, once again, I'm making this picture up completely. This order pair is at 0, 6. This point is at 5, 0. I also want you to put a point at 3, 2. Do what?
It goes just like straight down.
Well, it looks like this. We're going to connect these two, and then these two. Okay, now we're trying to minimize cost. So is cost restricted? Or can you spend as much money, I mean, without the concept of, you can write a check for anything for anybody, right? That doesn't mean it's unclear, but are you limited to what check you write? Could you actually put a pen on paper and write a $2 million check?
No.
You can, but will your bank account back it up? No. But in terms of debt, debt's not limited. You can keep acquiring debt. Just because you have a certain amount of debt doesn't mean it stops you from spending money. You can spend money and keep acquiring debt. Yes, ma'am. No. Because we're talking about a cost. So if you're a business, your cost is going to be out here. So what this would be represented would be is you have to spend at least this much money, you have to spend at least this much money on this, but there's no limit above. Okay, so it could go on forever. So our geometrical figure is technically going on forever this direction. And so it's an infinite size feasible region. So our feasible region is an infinite area. It goes on forever. But we still have 3 vertices. Okay? So we're going to take a look at each of those vertices. 0, 6. And we're going to plug each of these into the cost function. So to find the minimum value, we'll get 0 to 6. We get the cost is 30. Plugging in 3, 2. We get 9 plus 10, which is 19.
Yes, sir. Yes, sir. Nathan, Mr. Taylor needs to see you.
All right, so of these two, which is the optimal solution? 19, because we're trying to minimize, right? And 5, 0 gives us 15. Now remember, our goal is to minimize the objective function. Bless you. We're trying to minimize the objective function. So we take our vertices that we have as options, and we find out which one gives us the minimum value. So our minimum value, the minimum value of C equals 3x plus 5y is 15. And once again, this problem is not asking where it occurs at, but it could if it said, where does this occur? we would say this occurs at the order pair 5, 0. So once again, this occurs at.
So could you put like any number in that graph or what?
Yeah, okay, so you're saying could you pick a point out here?
Yeah.
Yeah, you can plug it in. Okay, and what you'll do is you can plug in any point in a shaded region and you'll get a cost answer. But the fact that I made on the previous page holds true always. No matter what point you pick, the minimum or the maximum the minimum in this case will always occur at one of these vertices. Okay, now this one doesn't have a maximum because this goes on forever. So cost doesn't have a maximum value. You can always find something that costs you more money because if you just bought one more of each, it costs more than the previous order.
So how did you get those points?
I'm making this up.
Okay.
This would be given to you.
Okay.
Oh,
Yeah, this whole picture is given to you. I didn't come up with this picture from the property.
So you just
That's just this would be like what you see here is what would be given to you as an assignment. Okay. Now the last example that we're going to do is a problem where the picture is not given to you. So example 3 is
well, we need a lot of this.
I'll dedicate a whole page. Given a set of constraints, find the optimal answer. And we'll just start off by we're going to do 2 examples of this. We'll do one right now, and then we'll do one at the start of class tomorrow, maybe. One right now might be sufficient. Here's the constraints. X plus 2y has to be more than or equal to 8. X has to be more than or equal to 2. Y has to be more than or equal to 0.
We just not like plug with points on that, right?
So, well, given a set of constraints, find the optimal answer. And then here's what we're trying to do. Minimize cost equals X plus 3y. So what we did yesterday is what we're going to be needing to do here. In order to know the optimal answer, we've got to know where the vertices are of the feasible region. In order to know where those vertices are, we need to graph a system of inequalities to come up with the feasible region. So step 1 is we're going to graph the picture. So we're going to graph each of these. Looking at this first one, what form is it in? Standard or slope-intercept? Standard. And since it's in standard form, we're going to use x and y-intercept to get the picture. We're going to ask to graph this. What's the x-intercept of x plus 2y? Greater than or equal to 8. It would be 8. You plug 0 in for y, 2 times 0 goes away, you get x equals 8. The y-intercept, you plug 0 in for x, divide by 2, the y-intercept is 4. So we're to graph this. Here's what we have so far. We've got the x-intercept is 8. The y-intercept is 4. We're going to connect these with a solid line.
You don't need anything under this.
Just a little bit. Okay, now it says x plus 2y is greater than or equal to 8. If we plug in 0, 0. 0 plus 2 times 0 is greater than or equal to 8. We get 0 is greater than or equal to 8. Is that true or false?
False.
That's false. So do we shade below or above?
Above.
We would shade above. So here's what we have so far. We've got this region being shaded.
Oh, this is gonna make a shape by itself like what we did on that model.
Yep, that's why we did that yesterday. Now, x is greater than or equal to 2. That's one of those special cases. It's a what kind of line? It's a vertical line at 2 on the x-axis. So we're going to go to 2 on the x-axis. We're going to draw a vertical line. And then the x values are greater than 2. Where does that happen? To the left or to the right of this line?
Right.
To the right of this line. So then now we're going to shade everything to the right of this line. So far, here's what we're talking about. Our feasible region is this region, right? That's the region that satisfies both equations. Now the last one, y is greater than or equal to 0. That's a horizontal line at 0. That's this line. And then we're going to shade everything, what? No, y, above or below? Above. So our feasible region for this entire problem is this area. That's the only region where we're above this line, to the right of that line, and above y equals 0. Does that make sense to everybody? That's just like that number 7 on yesterday's paper. You graph all of them on the same graph, and you only shade the area that corresponds, or they only shade the area that applies to all of them. Now, in doing that, we have found the feasible region, and when we draw the feasible region has vertices. There's 2 possible vertices in this picture. This geometrical object has 2 vertices. We know the one just by looking at the picture.
Like 63, right?
We know this one. Where's it at? 8, 0, right? So there's no algebraic work needed for that one. But the other one, if you weren't sure by looking at the picture, we don't know exactly where this is. We have to solve it using one of the other methods, either substitution or elimination. So what 2 lines make that? This up and down line, what's its equation?
Y is greater than 0.
Now up and down.
Oh. X.
So this is the x equal 2 line, right? And then this point is the intersection of the x equals 2 line and this slanted line, which is the x plus 2y equals 8 line. So to find where this ordered pair is, we're going to need to solve. To find where this point is, we're going to need to solve this system. The best method is substitution. We just plug 2 in. 2 plus 2y equals 8. 2y equals 6. What's y equal? 3. So we know what x is. That's right in the original problem. X equals 2. Y equals 3. So the ordered pair here is 2, 3. The ordered pair there is 2, 3. Now, the problem says find the optimal answer to this cost function. Minimize cost equals x plus 3y. The minimum answer will always happen at one of these vertices. So we want to know the minimum answer. We just take those 2 vertices that we just found and we plug them both in. Does that make sense to everybody? So we're going to go to cost equals x plus 3y. And we're going to plug in the point 2, 3. 2 plus 3 times 3, which is 11. And we're going to plug in the point 8, 0, which would be 8 plus 3 times 0, which is 8. So what is the minimal answer for cost? So the minimum value of c equals x plus 3y is 8. When we did that farmer problem, the scenario at hand, we weren't doing a minimizing problem, we were trying to maximize his fall income. So we were doing a maximizing problem. Okay, that's what we're leading into.